Okay, I'm going to work you through the lecture slides and everything. I'm going to try to do this in pieces so it's not a long video. And of course you can pause, so if I go too fast, you can listen to what I'm saying again. Okay. All right, so we're going to talk about what happens when we have unequal sample sizes in ANOVA. And then we're going to talk about multi-factor studies. So unequal sample sizes means that we have different sample sizes in each experimental condition that we have. So we don't have exactly the same number. I know we've done some analysis with that already this semester, but theoretically, we've only been dealing with equal sample sizes. So when we build our model, when we have unequal sample sizes, the decomposition that we have been talking about is not orthogonal. So we have to make a few adjustments when we actually calculate our sums of squares. So there's actually multiple types of sums of squares that can be calculated depending upon how you want to calculate it. So there's 4 types. So there's type 1, type 2, type 3, and type 4. So the type 1 sums of squares is when we have the orthogonal decomposition that we think of when we calculate ANOVA. So when we did the calculation by hand long time ago, like the second week of class, that was the type 1 sums of squares. So this is only appropriate when we have equal sample sizes in each treatment condition. So what happens is that when we have multiple factors in our study and we use type 1 sums of squares, the effects are tested in the order in which they are placed in the model. So if we have factor A and factor B, then factor A goes in first, and that's tested, and then factor B is tested, and then the interaction is tested. So if we have unequal sample sizes and the decomposition is not orthogonal, then when we put B in first, we'll actually get different results. So if we put B in, then we test for B, and then we test for A, and then we test the interaction, we're actually going to get different sums of squares when we put the factors in separate order. And we have unequal sample sizes. So that only happens when we have unequal sample sizes. If we have equal sample sizes, then the type 1 sums of squares will be the same no matter what order we put in the factors. So type 2 sums of squares are only used in designs where there's no interaction terms. Basically, it's a type 1 with no interaction term. So it's not really used that often because most of the time we want an interaction term. So the type 3 sums of squares are ones in which both effects are tested in relation to each other rather than in sequential order. So it doesn't matter how we put the factors in, we're going to get the same sums of squares. So this is the most powerful because order doesn't matter and interactions are important. One assumption we do make in this model is that interaction terms are more important than the main effects, which is true pretty much when we do analysis anyway. So that's just kind of implied when you're talking about type 3 sums of squares. And then you get to type 4, and then this happens when you have missing cells. So when you have like we'll see it later when we have missing treatment effects going on. That's what I mean by missing cells. So we don't have any subjects in a certain factorial design, like in a certain combination of A and B. So in like treatment 1 of A, and it's like 1, 3, so A and B, those crossings or something, if we don't have subjects there. So, but anyway, it's most of the time we don't even use type 4. Most of the time we use type 3. So when the designs are balanced, type 1, 2, and 3 will be equivalent, but when we have unbalanced design, we don't actually want to do type 1, and we can only use type 2 when there's no interaction, but then we use type 3 when there is interaction. So what we do in practice is that we always use type 3 sums of squares. Back when I was younger and studying these things, we actually looked at both types of sums of squares, and type 3 wasn't the default. Type 3 sums of squares is now the default in all analyses. It wasn't the default, so we actually had to tell it, hey, we need type 3 sums of squares, and we had to figure out the difference between 1 and 3. So you guys kind of missed that whole conversation now that you guys are learning it now, but We've been using type 3 sums of squares all semester, and you haven't even known about it because unless you noticed that the default says type 3 sums of squares. So it's pretty common to use type 3 sums of squares because it doesn't matter if the design is balanced or not. It's going to be the same to type 1, so you might as well just use type 3 because it's the safest approach. So we're going to just work through an example data set just so you can see the difference between the type 1 and the type 3, how the type 1 changes. So we have the cholesterol by state. We're not going to use the covariate. We're not going to use the age covariate. We're just going to have the cholesterol by the state just so we can have the one-way ANOVA. Well, actually, we're going to have two-way ANOVA because we're going to use the age group, but we're not going to use it as a covariate. We're going to use it as an independent variable and factor in the study just for our purposes of learning. Okay, so the two variables are age group and state, and the dependent variable is cholesterol, and we have 30 subjects. So here are the two levels. So it's a 2x3 factorial ANOVA with cholesterol as the dependent variable. So here are the sample sizes that we have in each treatment group. So you can see we already have a treatment group combination where we have 0. So that's fine to use type 3 sums of squares when that happens. So if we put in the state first, if you look at the sums, type 1 sums of squares that get estimated, for state it's 1,449, and then for age category it's 54,942. Now if we do it the other way and put age category first, then age category is 51,000 as opposed to the 54,000, and then state is 4,723. So you can see that they're definitely different, right? Where if you do type 3 sums of squares, here if you notice at the top it says type 1, here now it says type 3. If you see type 3 sums of squares, the state is 4687 and the age category is 53,013, and those will not change no matter if you change the order. So you'll always see a difference in the main effect sums of squares if you use type 1 and you have multiple factors and you have unequal sample sizes in each group. Okay, so basically, the moral of the story is use type 3 all the time. So back when this book was written, there was actually a discussion, but in practice we use type 3 sums of squares all the time. So I'm going to show you how to do that later on how to get the different types of sums of squares when we do SPSS. Actually, I can do that right now and then have just a separate video for the second half. Okay, so I'm going to go to SPSS, and if I go to my data file, I have it saved as state.sav. So I'm going to go to state.sav, and here's my data file. So you notice I have the 3 variables, state, age group, and cholesterol. So that's my 2x3 design. And I'm going to get the different sums of squares. So I go to Analyze, General Linear Model Univariate. Of course, you can pause if I'm going too fast. Dependent is cholesterol, state, and age group are moved over into the fixed factors. Once you go to the model statement, if you look, here's sums of squares. You're going to move type 1. We'll change it to the type 1, or we could do type 2, type 3, type 4. So we'll just change it to type 1. You see I put state in first. So this is the model with state first. I'm estimating the full factorial model. I just want the sums of squares table so I don't have to worry about doing any other options. So if I go to my output, I get that state and age group here, the 1,800 and 40,000. Why does this look kind of like a different number than what was in my slides? Is that? That's weird. Type 1. Let me see. Maybe I changed the number by accident. Oh well. I just ran that. That's really weird. State, age group. Okay. Anyway, maybe I coded it differently. So let's not worry about that. Let's go back to the data set. We'll just rerun it with putting age group in first. All the purpose of this is just looking at the differences of sums of squares anyway. So we will take this out, put age group in first, state in second, have type 1 sums of squares, and we see that they do in fact change. We see a 34,000 for our age group where it was 40,000 here, and a 7,600 instead of an 1,800. So we have different, we have different sums of squares for each of the groups. Okay, so basically you'll get different sum of squares if you don't do type 3. Okay, so that was that story. Let's do that. I'm gonna go ahead and stop this video and upload it, and then you'll have a separate video for the second half of the lecture.